Assalamualaikum and hello. I am from University Technical Malaysia Melaka. Now I want to explain about my research about machinability study of roughing machining strategies for pocketing features of an aerospace. And my name is Muhammad Mahfiz bin Sabardan. My number metric is B0919100046. And my supervisor is DR.TS SYAHRUL AZWAN bin SUNDI. For content on my slide, I will start with introduction about background, problem statement, objectives, and scope. And next, literature review. I will explain about machinability and material I select, machining strategies that I do, surface roughness that will affect the material, measurement of geometry. For methodology, I will show about my flowchart, my CAD/CAM simulation, and my machining. For preliminary result, I will explain about my compilation data and my PS1 Gantt chart and my next SEM PSM2 Gantt chart. So we will start about introduction. In my slide, the background of my research is we know milling is an important step in the manufacturing industry since it ensures high productivity and quality are constantly in demand, and mechanical milling is frequently utilized technology in the industry sector because to its adaptability and precious in product manufacture. Next is my problem statement. For first problem statement, high demand for high quality pocketing feature for surface roughness, and number 2, dimensional accuracy in the milling process and cutting strategies. My objective is to evaluate the effect of roughing strategies, namely multi-file and crocodile, on the surface roughness and dimensional accuracy in machining pocketing profile of an aerospace structure part. Number 2, to determine the most optimal roughing strategies to machine pocketing profile of an example aerostructure part using an actual aerospace standard material, that aluminium 0161 series, with respect to the surface roughness and dimensional accuracy utilizing roughing operation offered by CATIA V5. For my scope, in this project, I will use CATIA V5 by focusing on roughing operation by applying concentric two machining strategies, namely multi-path and crocodile. Next, I will generate a complete CAM program with the cutting strategies in place is then post-process by using integrated post-processor which compatible with Siemens 840DC control. And I will use the machine of in this institute DMG that name DMG Mori DMU 60 Evo, a CNC milling machine. 3 axis is going to be used to be performed the physical machining for both machining. This is my literature review. For machinability, machinability may be described as the simplicity at which a metal could be machined or machined in a material removal process under particular circumstances. However, the pace is difficult to define because the multivariable and non-qualitative assessment that incorporates the machining variable. One of the most popular machining procedures in the industry is aluminum alloy machining. Aluminum, in compared to steel, offer lower cutting force and may be machined at greater cut speed. The influence of metallurgical characteristic, heat treatment, and cutting circumstance on essential machinability parameters such as tool wear, surface quality, cutting force, and chip formation will be shown in brief overview of my literature review of machinability of aluminum alloy. Next is material characteristic of aluminum 6061 series. This aluminum is part of 6000 series of alloy. As a result, magnesium and silicon are the primary alloying elements. Magnesium is used to boost strength, whereas silicon is used to lower the melting temperature of the metal. The rule for the chemical composition of 6061 aluminium can be found here at my left side. Aluminium 6061 is widely used in a range of technical applications, including transportation and construction, where strong mechanical properties such as tensile strength and hardness are required. The chemical composition of aluminium 6061 is shown because of its high corrosion resistance. It is an ideal contender for maritime structural applications. The quest for less weight, cost-effective, and high-performance materials for 6061 aluminium usage in a number of structural and non-structural applications has led to the development of metal-metallic composition. For machining strategies, the pathway that a cutting tool follows to remove material and build a shape are known as machining technique. It is made up of a sequence of coordinates that indicate how a tool travels during machining. Next is my machining strategies. I will use helical in these machining strategies because in helical mode, the management of the non-cutting diameter has been enhanced, especially in the computation of wrapping technique. Inward, outward, or both helical motion are possible. Next, my machining strategy is concentric. Concentric roughing is a custom machining technique that provides cornering capabilities and allows customers to produce tool parts that are optimized for their HSM machine. Other cutting techniques include not entirely burying the tool in the materials, routed internal corners and loops added to exterior corners akin to zigzag machining. This is my example of two-path concentric. Next, my machining strategy is Torquedan. TPC standard for Torquedan performance cutting, which is a cutting tool idea suggested by a number of tool manufacturers. The design is based on a variable length for front cutting edge and an unique helix angle to provide the lowest possible variation level, which correlates to higher surface quality. Even in a roughing direct finishing process, the chip thickness profile is not consistent in troquide milling process because each troquide circle has varied cutting stress. And this is my two path of troquedan. So next is surface roughness. During the milling process, surface roughness is an essential feature that reflects workpiece quality. For example of research past, Munoz, Escalona, and Maropaulo devised multiple regression approach, fuzzy set-based methodology, and artificial neural network prediction of surface roughness (RA) value in aluminium alloy of 7075 T7351 series in the first milling machining process for various ANS. Surface roughness has a big influence on the machine accuracy, mechanical item performance, and manufacturing cost. The manufacturer adjusts the cutting condition to obtain the appropriate surface roughness for these users. The desire for high quality, completely automated manufacture focus on the product surface condition, particularly the roughness of the machining surface because it is impact product look, function and dependability, as well as the prevalence of tolerance and surface finish consistency. Next is geometrical measurement. In the first step, the measurement of surface quality obtained from CAM software was conducted. After the geometric characteristics of the produced part were measured with the use of CMM device we shown below, circular measurements that were also used to measure the bottom of the component. This is my example of CMM device and the operation. So next is methodology. In my flowchart, I have three phases. In the first phase, the CAD model was modified to preserve the concept of the product for machine and model suitability. The process continues with the machine accelerator geometry and machining parameters. Cutting parameters for all parts remain constant and include the length of the tool reach, depth of cut, feed rate, and spindle speed. Lastly, finishing the program to proceed to the next phase after determine the machining strategies for roughing and pocketing. For the second phase, the 3-axis CNC milling machine was chosen for the project because of the simple part. Aluminum 6000 series have been used in the research facility according to the material used in the aerospace or aircraft industry. When there is no error on CAD file or CAD part that have been modified, the process will have continued with set up the material WPC and physical machining process. After program and surface roughness will be tested and the machining accuracy will be measured and analyzed. And lastly, for the third phase, collecting data and result of the surface roughness and the machining accuracy, all the documentation will be reviewed by supervisor then will be submitted for calculation of final year project marks. Next is modifying CAD. For the first step, cutting off. The right and middle side of the aircraft rib will be removed by cutting off. It is because the right of the portion already has a pocketing profile. As a result, the part shrink to a fraction of at its original size. Scaling. The scaling process was carried out to ensure that the part was compatible with the size of cutting tool available. For each axis, a scaling process was prepared. Scaling process will prepare for all three axes which are x 0.45, y 0.50 and z is 0.5. Next is stock. The size of the stock are 110 mm and multiplied by 130 mm and multiplied by 20 mm. And next is axis system. Axis system WCC01 will be created at the stock. Next is plane system. The approach 20 mm plane has a yellow color and the approach 100 mm plane has a magenta color. It also includes one point in the plane approach center and a new axis system. Assembly. In assembly design is a new file was created to combine all of the stock and axis system and plane system. The two axis system happen to be updated at the same time for a better understanding. Next is scan process. Firstly, process roughing 1. The facing technique was utilized to remove surplus material from the stock surface as seen in the figure right side. Mill D63 was used to complete this process. Process roughing 2. To acquire a roughing outline of that portion, the roughing procedure was used. It had been completed with the use of exterior roughing. Profile contouring can also be used to eliminate material from the area surrounding of a part. The tool and mill D16 diameter was used for these two procedures. Process semi-finish 1. To create two roundness shape in the center of the part, the pocketing procedure was used. It was done with the end mill D8 tool. The details are for the machining operation and shown in figure right. Next is process semi-finish 2. To achieve a rectangular shape, the pocketing procedure was utilized to remove material from the right and left side of the item. It was also utilized to make two rectangular shapes at the center for the roundness. The tool D10 was used to do this pocketing operation. Lastly, process semi-finishing. Profile contouring is a finishing process that is employed as the final step in the production of a finishing object. Mill D3 was used to complete the task. And lastly, machining setup. Before beginning a machining process, the machining must be set up. It aids in the avoidance of an unavoidable situation or accident. The item was held in place by a fixture during the machining operation. Next is preliminary result. In my compilation data, for surface roughness, the parameter that was investigated in the surface roughness was the value of RA. RA, RY, and RZ are the three parameters derived by the surface roughness testing. However, because RA is utilized as a global measurement of the roughness executed on a profile, defect in material surface can develop during or after processing, and analysis is required to provide the information needed to improve surface effectiveness, efficiency, and durability. Lastly, the machinery measuring was used to examine a part produced by machining. Aside from it, the piece was divided into half, one circular and other rectangular. The rectangular shape was studied using positioning, where the circular shape was analyzed using dimensional roundness measurement. Okay, that's all, and this is my Gantt chart for my whole PSM 1. And then is my Gantt chart for my PSM 2. Okay, that's all. Thank you.